Let's start with a quote by Nancy G. Levison. Viewing accidents as chains of events and conditions may limit understanding and learning from the loss and omit causal factors that cannot be included in an event chain. Now, in the first section, we diagnose the problem, the 5 whys, when pointed at human systems produces blame instead of learning. We walk through a story watching it happen in real time. And now we need to understand more about why this happens, not just that the tool fails, but why it fails at a structural level. Because once you understand the mechanism, you're never going to look at investigations the same way again. This lesson is going to focus on the deepest assumption embedded in the 5 whys, an assumption so fundamental that it often goes unquestioned. And that assumption is linear causality. We've talked about this a bit. The belief that failures occur as chains of cause and effect. A happened, which caused B, which caused C, which caused D, and if you keep pulling that thread, you eventually arrive at a single root cause. This assumption feels intuitively correct because it matches how simple physical systems behave. So there's a reason why it feels right. But the distinction between systems where linear causality actually holds and the complex, adaptive systems in which most organizations now operate is one of the most important distinctions in modern safety science. Linear causality does exist in certain environments, and it's important to acknowledge where it works. If you drop a glass and it shatters, to a certain extent the causal path is clean. Gravity accelerates the glass. The glass strikes a hard surface. The impact exceeds the tensile strength of the material. The glass breaks. Each link is observable, measurable, and repeatable. Under identical conditions, the same outcome reliably occurs. This is a deterministic system with a linear causal structure. The Toyota production system emerged largely in this type of environment. When a machine stopped, a physical component failed. A fuse blew, a bearing seized, a pump shaft wore down. Each failure had a direct mechanical relationship to the next. When the faulty component was repaired, the problem was resolved. Manufacturing systems in the mid-20th century were complex in scale, but they were largely decomposable. The whole could be understood by understanding its parts. Relationships were predictable and cause and effect were stable. Now consider the systems most of us work in today. Charles Perrow, a sociologist at Yale University, fundamentally changed how we think about failure with his 1984 book, Normal Accidents: Living with High-Risk Technologies. Perrow argued that in systems characterized by interactive complexity and tight coupling, accidents are not anomalies. They're inherent features of the system itself. In such systems, multiple small and seemingly insignificant events interact in unpredictable ways. Failures do not propagate along a single path. They emerge from the interaction of many components, decisions, and conditions. There's no single chain to follow because the failure was not caused by a chain, it was caused by a web. This has profound implications for root cause analyses. If a failure emerges from interacting factors, but your investigative method can only trace linear chains, then the method is structurally incapable of explaining what happened. The limitation is not with the investigator, it's with the tool. Nancy Levison, who we quoted at the very beginning, she was a professor of aeronautics and astronautics and engineering systems at MIT. She extended this insight into modern safety science. In Engineering a Safer World, she explained that traditional accident models assume failures are caused by broken components or unreliable operators. While this assumption held in relatively simple electromechanical systems, it no longer holds for modern socio-technical systems. Levison writes that viewing accidents as chains of events limits understanding and omits causal factors that cannot be represented in a linear sequence. This is a critical point. Chain-based models do not merely miss causes, they make certain causes completely invisible. She further observes that root cause analysis often stops at the first cause that's familiar, easy to act on, or politically acceptable, frequently the human operator. This doesn't happen because investigators intend to blame individuals. We hope not, right? It happens because linear tools converge on endpoints, and people are always available endpoints. Levison also highlights a structural trap. Insisting that operators always follow procedures does not guarantee safety, but it does reliably guarantee that someone can be blamed when things go wrong, whether an operator follows the procedure or deviates from it. A chain-based analysis can always frame the outcome as human failure. To address these limitations, Levison developed STAMP STAMP, the Systems Theoretic Accident Model and Processes. STAMP treats safety as an emergent property of the system, arising from interactions among components rather than from component reliability alone. Emergent properties cannot be understood by decomposing the system. They require a systems-level perspective. Eric Hollnagel captured this problem with his WYLF-IWYF principle. What you look for is what you find. Investigation methods do not simply reveal causes, they shape what investigators are able to see. If a method assumes linear causality, it will produce linear explanations. If it assumes individual error, it will identify individuals. Not because it's right, not because those explanations are correct, but because the method constrains the outcome. Hollnagel adds an essential corollary. What you find is what you fix. When investigations identify people as causes, organizations respond by retraining, disciplining, restricting, or removing. Meanwhile, the systemic conditions that enable the failure remain unchanged. Hollnagel's research with Lundberg and Roland-Hagen demonstrated this effect empirically. Across multiple accident investigation manuals, the underlying accident model determined the types of causes identified. The method shaped the story. Hollnagel further argues that accident investigation is a social process. Causes are constructed and agreed upon, not discovered as objective facts. The story that emerges reflects the assumptions embedded in the investigative framework, Safety 1, Safety 2, and the myth of the root cause. Traditional safety management, what Hollnagel calls Safety 1, defines safety as the absence of failure. It is reactive and event-focused. Safety 2, by contrast, defines safety as the presence of conditions that allow systems to succeed under varying pressures. It studies how work actually gets done, including the adaptations that normally prevent failure. The 5 Whys is a pure Safety 1 tool. It activates only after something goes wrong. It cannot see the daily adjustments that keep systems functioning, nor the conditions that make those adjustments necessary. This leads to a final critical insight. There is no such thing as the root cause in a complex system. Failures in a complex system are produced by multiple interacting conditions. Each condition may be necessary, but none is sufficient on its own. Declaring a single root cause means selecting one explanation and discarding the rest. Often, the systemic conditions that offer the greatest leverage for prevention. The 5 Whys will always produce an answer. That's what makes it appealing. But producing an answer is not the same as producing understanding. It's not the same as being productive in terms of accomplishing the ability to prevent the problem from happening again, or finding out what the problem actually was or is. Preventing future failures requires tools capable of seeing patterns, interactions, and emergence, not just chains. In the next lesson, we'll examine one of the most powerful mechanisms that drives blame in investigations, language. We'll explore more about why asking why produces different outcomes than asking how or what, and how just that single word change can shape an entire investigation.